Hello everyone, welcome to the another lecture of Alcohol, Phenol and Ethers. Myself is Suman Singh. So in the last class we were discussing about the preparation of phenol from we have seen from cumene, right? So now today we will see the preparation of phenol from Grignard reagent. So as you can see here we have taken here a benzene, and with that benzene suppose one halogen group is attached here. So in the presence of Mg and ether, as you can see, in the presence of Mg and ether, it will form what? It will form this Mgx, right? Now after that, when you will oxidize this, it will form OMgx. Now in the presence of H2O, here what will happen? H positive from H2O will go and react with this Mgx, okay, and it will form phenol here, okay. One example is here, as you can see, when we have written here chlorine is attached here and here CH3 is attached here. So in the presence of Mg and ether, what will happen here? This will attack to this, right? Here it will form what? MgCl, as you can see. CH3 will be as it is, though there will be no change in CH3. After that, when the presence of O2, we will get what? OMgCl, right? It is same, right? Now in presence of H2O and H positive, we will get here phenol, right? So I hope you have understood this. Now for the next one is from phenolic acid, which is also called decarbolization. Here carbon ion stability we have to see, right? So what we have taken here, as you can see, we have taken here OH is attached and here COOH is there. So first of all, with in the presence of NaOH, we will get what? We will get this, okay, ONA. Now after that, what we will do, in the presence of NaOH and CaO, and when we will heat this, we will get ONA, right? And after that, in the presence of H2O, or when we will hydrolyze this, we will get this phenol, right? So some of the example is given here, as you can see. One more example is given here. So what you have to see here, in place of COOH, what you have to see here, in presence of COOH, H has came, right? Here also you will see in presence of in the place of COOH, this H group has attached here, right? Now here also you can see that in place of COOH, H has came, right? So I hope you have understood from the phenolic acid. So here is some of the question is there, you can notice this one. Now again, preparation from aryl halide. So in the aryl halide we have taken what? Chlorobenzene in presence of NaOH and high pressure, and in high pressure and high temperature, pressure should be around 250 atmosphere and the temperature should be 400 degrees Celsius, okay. So at that time it will produce what? ONA positive, ONA, and after that, when in the presence of hydronium ion, or when we will hydrolyze this, we will get here phenol, right? So here electron withdrawing group will increase the rate of substitution, okay. Now so one more example is there, we have taken here Cl, here NO2, here NO2 and here NO2. So in presence of H2O, we will get what? Picric acid, as you can see, NO2, NO2, NO2 and OH. So this is what is a picric acid, right? So I hope you have understood this, how to prepare phenol from the following reagents. Now after that we will see the physical property. So you all know that phenols are what? Colorless, toxic, corrosive and needle shaped solid, okay. And phenol soon liquefies due to high hydroscopic in nature, okay. As you can see, example is there. And after that, when we talk about the solubility, the phenol is less soluble in water but widely soluble in organic solvent, okay. Now again, when we talk about the simplest phenol, because because of the hydrogen bonding have a quite high boiling point, okay. And when we talk about orthonitrophenol, is steam volatile and also is less soluble in water because of intermolecular hydrogen bonding, okay. Now next is reactions of phenol, or we can say the chemical property of phenol. So first one is nitration. So this is also given in your syllabus. So nitration, so what we have to do when we are using when we are doing with the nitration, so at that time you have to notice that what we have used here, we have used here on phenol, okay, and in place of phenol what we have used here, dilute HNO3, right? So when you are using dilute HNO3, at that time two product we are getting what, ortho nitrophenol and para nitrophenol, right? Ortho nitrophenol and para nitrophenol, okay. After that again, when we are using here concentrated, okay, concentrated HNO2, at that time we are getting what, picric acid. As you can see, we are getting here what, picric acid, right? So now next, the very important thing which you have to see here is that, as you can see here in this case, when we are using here this, so in this place, in the place of H, what is come, what will happen, in place of this NO2 will go and attack to this H, okay, and you will get this, right? Now here, so I hope you have understood this, right? It is very simple, right? So when you will use here dilute HNO2, you will get ortho and para nitrosophenol. Here when we are using concentrated HNO3, at that time we are getting this picric acid, okay, and as you can see here, right? So these are some questions you can practice at home. The answer is also given here. Now next is sulfonic acid. So sulfonic acid is very easy, just you have to see what we are using here, phenol. As you can see here, we are using here phenol in concentrated H2SO4. In presence of concentrated H2SO4, two products will form, okay. So either this will form, okay, or this will form, okay. So but you have to see the difference when you are using here temperature 25 degrees Celsius, where at that time the SO3H is attacking to the ortho position, right? But when we are using here 100 degrees Celsius, at that time it is attacking at a para position. So always remember that when they will ask the question, or when they will ask you to find the product, at that time always remember that what is the temperature is given here. When it is given H2SO4, at that time if the temperature is given 25 or less temperature, in less temperature the major product will be on the ortho position, okay. And here the here the major product will be under kinetic control process, okay. And when we are using a high temperature like 100 degrees Celsius, at that time our major product will be this para position. SO3H will attack to the para position, okay, and the major product under and here the major product will be under thermodynamic control process, okay. So I hope you have understood what is sulfonation, okay. Now next is, here is some questions you have to predict the product. So as you can see, we have done some of the questions, so you can practice at home this one, right? Now next we will see aspirin formation. So for aspirin formation, what we are using here, we are using salicylic acid. As you can see here, we are using here salicylic acid, and here we are using CH3CO2H, and this one, in presence of this we will get what, we will get acetyl salicylic acid, which is called aspirin, and this will come out from the reaction, okay. So as you can see what is happening here, this will be remain same as it is, okay, but here in place of this H, okay, in place of this H, this will attack to this H, and you will get this one, okay, and this will come out from the reaction. So as you can see here, right? Now next is very important, Reamer-Tiemann reaction, okay. So we will discuss about Reamer-Tiemann reaction. Again what, phenol here, and in presence of CHCl3 and aqueous NaOH, okay, we will get an intermediate, this one ONA, Na positive, O negative, Na positive, and after that in presence of NaOH we will get this, okay, one CHO group will introduce here. As I have already told you that in the presence of aqueous, sodium hydroxide followed by the hydrolysis and aldehyde group, as you can see, aldehyde group is attached into the ring, is get introduced in the ring at the position of ortho. This is an ortho position, right? At the position of ortho, okay, and to the phenolic group. Now after that, when we further hydrolyze this in the presence of H positive, we will get salicylic aldehyde, okay. So we will see the mechanism, what actually it is happening here. I hope you have got some idea. So we will see the mechanism. So in the first, what is happening here, you see this is what CHCl3, right? C sorry, CHCl3, right? So in CHCl3, this chlorine and this chlorine, let me write here so that you will understand clearly. Suppose we are taking your CHCl here, Cl here and Cl here. So these three are what? These three are electron withdrawing group, right? So since they are electron withdrawing group, so what will happen, more and more electron will shift towards them, right? So what will happen, this will carry a negative charge here, right? Negative charge here, and this hydrogen will carry here positive charge, right? Selfly positive charge. So now what will happen, the OH first of all will come and attach to this hydrogen. Okay, so when OH will come and attach to this hydrogen, what will happen, we will get what, we will get CCl3 negative, right? Now after that, since CCl3 negative is very reactive, so what will happen, the one Cl will come out from here, from this CCl3, from CCl3 one chlorine will come out. Okay, and we will get a carbene, as you can see, CCl2. Okay, this will behave here, this carbene here, it will behave as an electrophile, right? So now we have got here carbene. So what will happen next here, the as you can see, this carbene has now 6 electrons, right? And here what will happen, this, since it is carrying a negative charge, so this bond will shift here and this electron will come and attach to this hydrogen, right? So when this will come here and this double bond from here, so electron will go and attach to this. So at that time what we will get, we will get this, as you can see here, right? Here double bond, we will get here double bond. After that, here we are getting CCl2, here negative charge, and here hydrogen, right? Now after that, what will happen, in presence of H2O, and OH will come out from the reaction. Okay, so from here OH will come out, as you can see. uh, we will add H here, right? So here you can see, from by adding H2O and OH negative, we are getting what, this. Okay, one H has been attached here. You can see here CHCl2, here it was CCl2, now we have came with CHCl2. Now there will be a tautomerism of this. Okay, so at that time we will get this. Okay, after the tautomerism. Now again, in presence of aqueous KOH or NaOH, anything, we will get here one aldehydic group will come and attach to the ring, and this will carry a negative charge here, as you can see here. Now after that, in presence of H positive, we will finally H positive will come and attach to this oxygen. Okay, and we will finally get salicylic aldehyde, right? So I hope you have understood the mechanism. Now next is, if we are using here OH and CS3 in presence of NaOH or CHCl3, so at that time we will get this here, this will be the main product, and this will be the non-aromatic product. Okay, this will be around 18%, and the rest it will be this, right? Now again, if we are using here this one, if we are using here this, and in presence of NaOH and CCl3, we will get this only, we will not get any non-aromatic product. Okay, so I hope you have understood this, right? Now next we will see Kolbe's reactions. Okay, so this is also very important for your exam. So here, when sodium phenoxide, here when sodium phenoxide is heated with carbon dioxide at 400 degree Kelvin, 400 Kelvin, and under 4 to 7 atmospheric pressure, sodium salicyclate is formed as a major product. Okay, and this on acidification give salicylic acid. Okay, and always remember that the small amount of para isomer is also obtained, and if the temperature is allowed to rise about 410 Kelvin, the para isomer dominates. Okay, so this type of reaction is called what, Kolbe's reaction. So we will see what is happening here. When we talk about this, here we have taken phenol in presence of CO2 and NaOH. When we will heat this, we will get this. Okay, C double bond O, C double O negative will come out, and after that, in the presence of H positive, we will get salicylic acid, right? So here always remember there are 2 points which is a very important. Here electrophile is this is our electrophile. Okay, double bond O, double bond O, here it is negative, here it is positive. Okay, so this is the electrophile here. Okay, so and the medium of the pH, the pH of the medium should be greater than 10. Okay, I hope you are understanding this. So here what we have got, the medium of the pH should be greater than 10 and the electrophile will be this here, right? So we will see the mechanism. So and the product will be acidic, as I have already told you, right? The product will be acidic. So what is happening, we will see here. First, in the first reaction, as you can see, when we are taking here phenol, at that time OH will come and attack to this hydrogen. Okay, so when OH will come and attack to this hydrogen, at that time what will happen, the OH will carry here negative charge, right? Like this, the OH will carry here a negative charge like this. Okay, so what will happen, this negative charge will come here. After that there will be a double bond, formation of double bond here, and since we are using here electrophile, this one is our electrophile. So what will happen, this will attack, right, to this will attack to this. So when it will attack to this, it will form a compound like this. As you can see here, it will form a compound like this, right? Now after further, when it will rearrange, what will happen, if it will, when it will form like this, at that time what will happen, this is an intermediate product. Okay, so after that what will happen, there will be a rearrangement. Okay, so when there will be a rearrangement, as you can see, this double bond is shifting here and this negative charge is attacking to this carbon. Okay, so at that time what we will get, this Na positive will come out from the reaction. So at that time we will get here this, as you can see, this will be double bond as it is. Okay, and this one here we have got this carbon, as you can see here we have got the carbon and double bond here, right? As you can see, right? Now after, in presence of hydronium ion H3O positive, after in the presence of hydronium ion, we will get, there will be a rearrangement again. This electron will shift here, this double bond will shift here, and this negative charge will come here and attack to this hydrogen. And after that there will be a rearrangement, we will get here OH, as you can see, and this two OH, this one and this one will be as it is, as you can see, and we will get this, right? Now after that, further there will be a rearrangement and we will get here salicylic acid, or this is a salicylic acid. Okay, right? I have written 2 times. So I hope you have got some idea about the mechanism. Okay, so one more mechanism, if you have one more example you can take. Suppose you can take like this also, if we are getting confusion, then if this is our benzene or this is OH, phenol is there. So in presence of suppose NaOH, in presence of NaOH, we will get this. Okay, we will get this, we will get this here, we will get O, here we will get Na will be plus and O will be minus, and there will be a lone pair 1 2 3 4. Okay, and after that what with the what was the electrophile here, we have this, right? Here O, here again O. So what will happen, this double bond will go and target to this. Okay, and this bond will shift here. Okay, so what will be the product, I am writing here again. So we will get here intermediate like this intermediate you will get. Suppose we are here with the double bond here, one bond here, and this will be O here. After that lone pair 1 2 3 4. Okay, and here will be hydrogen, as I have already told you, and here C double bond O, and here O, Na positive will come, right? And here will be 1 2 1 2 3 4 lone pair. Okay, 1 2 3 4 5 6 and negative charge here, right? So this will be the intermediate. After that further, when you will in the tautomerize, when you will tautomerize this, we will get minus H positive will come out and plus H positive will be added, right? So what will have, what will be the product, I am writing here. So product you will get like this, not product, the intermediate sodium salicylate we will get here. So this will be like this. Okay, here OH and here O N A. Okay, positive, here O is negative, and here double bond O. Okay, and here lone pair is there. So after that further H positive will come out. When you will get H positive, we will get final product, which is salicylic acid, which is this. I hope you have understood. Now you have understood the mechanism, right? Those 2 examples I have given you, we have got here salicylic acid, right? So this was about the understood this, right? So here are some of the examples, as you can see. Right now, next we will see Friedel-Crafts reaction. So in Friedel-Crafts reaction, there will be two types. One will be alkylation, and another one will be acylation. Okay. So in alkylation, what is happening here? You can see we are taking here phenol, and we are taking here CS3Cl in presence of AlCl3. So it will be more. It should be 3 mole. And when you will heat this, you will get this minor product, and here you will get major product. So always remember that in alkylation, the major product will be the one which will be in the para position. Okay, if CS3, if here you are using CS3, if this CS3 is in the para position, okay, as you can see here, then this will be the major product in acylation, in Friedel-Crafts reaction. Okay, and here what we have to do, we have to use here AlCl3 in excess, or means what, if we are using here 1 mole, then it should be minimum 3 mole. Okay, so what will happen at that time, the major product will be the one, the way here where the CS3 is in the para position. Okay, and when it is in the ortho position, it will be the minor product in alkylation. Okay, now again when we talk about the acylation, so here again when we are using this phenol in presence of this, we are using AlCl3. When we are heating this, again the minor product will be what I have told you, the ortho product, the when the one, if this one, if this group, okay, if this group is in the ortho position, as you can see here, if it is in the ortho position, then it will be a minor product, and if this group is in the para position, it will be a major product here. Okay, and the reaction is very slow. Why? Because the reaction is very slow because of the formation of this, the reaction is very slow, right? So when this Friedel-Crafts reaction, the extension of this Friedel-Crafts reaction is also called what? Fries rearrangement. Okay, so always remember that in Fries rearrangement, at low temperature, para will be the major product. Okay, and at high temperature, ortho will be the major product. Okay, now again when we talk about the ortho position is occupied, if the ortho position is occupied, then only para product will form, and if para position is occupied, only ortho position will form. Okay, then only ortho product will form. So as you can see here, we have taken here this. So here electrophile is this one, as you can see, RCOOCOO. Okay, here this is an electrophile here. So when we are talking here AlCl3, and when we are hitting this, at that time what will happen in place of this H, this one, here you can see we are getting this, right? Here we have got OH, and this will come here, and further this one, and here we will get this. Okay, means what is happening here, what we are taking here, we are basically, we used to, when phenyl acetate. Okay, here basically when phenyl acetate is heated with anhydrous AlCl3, okay, it undergo a rearrangement. Okay, now it go in rearrangement in which acyl group migrates from the phenolic oxygen to an ortho and a para position. Okay, forming ortho para hydroxy ketone, and this reaction is called what? Fries rearrangement. Okay, so I hope you have got some idea about the Fries rearrangement. One more example I would like to give you. Suppose this for this one I will write here. Suppose we have this, here is our, suppose OCOCH3. So this is what, this is phenyl acetate, right? So this phenyl acetate in presence of AlCl3. Okay, and when we will heat this, at that time we will get what? We will get what? Ortho hydroxy ortho hydroxy acetophenol, and after that we will get para hydroxy acetophenol. Okay, when we will heat this, we will get two product here. One will be this, which I have already written in the downside, as you can see, COCH3. Okay, and here OH, and one more product we will get, this. Okay, this is what, here also ortho, and here you can see it is on the para position, right? COCH3. So this one is what? Ortho hydroxy acetophenol, and this one is para hydroxy acetophenol. So this type of reaction is called what? Fries rearrangement, right? So here low temperature para product will be more major product, and if there is a high temperature ortho product will be a major product, right? So as you can see, I have also done the mechanism here. So when you take here AlCl3, so if you are taking this, what will happen? This O will come and attach to this Al. Okay, so at that time we will get this. As you can see, it has already attached to this here, right? So after that, what will happen? After the formation of this bond will break and it will go and attack here. This bond will come out like this. It will be like this. So at that time, what will happen? We will get this, right? We will getting this. So what we have here, we have discussed about the electrophile, right? This is our electrophile. So if it will either it will attack from the ortho position to this carbon, or it will attack from the para position to this carbon. Now what is the difference? If the temperature is very high, as you can see 370, so at that time major product is ortho product, right, as it is attacking to the ortho position. Now again, when the temperature is low, suppose room temperature, at that time it is attacking to the para position, right? So I hope you have understood this. As you can see, this one we have take what this is what phenyl acetate, right, or phenyl acetate type. Here what we have taken AlCl3, so when it is reacting, it is forming like this intermediate. So after that, when it will rearrange themselves and it will form like this, because double bond from here it will go up, right? Double bond will break here. So here it can now this one, the one which is formed here, it can either attack to this carbon, to this, either from the ortho side or from the para side, to this carbon, either from the ortho position or from the para position. So if the temperature is very high, it will attack to the, or the product will be ortho product, and if the temperature is low, suppose room temperature, the product will be what? Para product. Okay, so I hope you have understood Fries rearrangement, right? Now after that is Alps persulfate reaction. It is also called PHAF reaction or FATA reaction. Here it is very easy. In presence of K2S2O8 and in presence of KOH, we are forming here quinol. As you can see, it is just attacking to this here. Suppose this is what this, suppose it is for this OH, this is suppose ortho, meta and para, right? So always remember the OH, where the OH is here in the same position, para the another OH will come and attach, right? So one more example, as you can see, here the OH is here, so just here the product will be OH will come here, right, as you can see, and CH3 will be as it is, it will remain as it is. So this type of reaction is called what? This is called Alps persulfate reaction or FATA. Now next is, after that is Lieberman's test or Lieberman's reaction, okay, or it is also called, sometimes it is also called nitroso test. So as you can see here, most of the phenol give this test, okay, and here what we are basically what we are doing here on warming this concentrated H2SO4 and sodium nitrate, okay. Here phenols give a red or brown coloration, and the color changes to blue or green by adding an aqueous NaOH, okay. Now here phenol react with nitrous acid to give what? Para nitrosophenol, which rearrange to quinol, and in the presence of a concentrated H2SO4, quinone condenses to phenol to give what? Idophenol, which is red in color, while if you are taking the excess of NaOH, sodium salt of idophenol is obtained, which is blue in color, okay. So you can see the example here. So as you can see, we are using here 2NaNO2, okay, plus H2SO4 plus H2SO4. So we are getting here Na2SO4 plus 2HNO2, right? So now as you can see, this one, and when we talk about this one, right, here what is happening, you see it carefully. Here H2O will come out, this H2O will come out from here, okay, and we will get a product like this, as you can see here, right? H2O is coming out, right? Now after that further, well, here this is what is called para nitrophenol, right? Now after that further, it will rearrange themselves, and we will get like this. Okay, after when it will rearrange, so we will get like this the product. Now after that, further in one more, this phenol will come and attach to this. So again hydrogen will come out from the rear, as you can see, minus minus H2O I have written, right? So again when H2O will come out from here, so at that time we will get the product this. Okay, get the product this. Now further when we are using here NaOH, and here again H2O will come out, and we will get this product, final product, which is blue in color, which is also called a dye, right? So you can see here we are using this, right? We are using this one. What is happening here, this O is coming, this negative charge is coming here. Okay, so at that time when negative charge is coming here, this double bond will shift here. Okay, as you can see here, let me zoom it so that you can see it correctly. As you can see, this one is shifting here, this one is shifting here, and this will shift here. So what will happen, this will change into this, like this, it will change into like this, right? As you can see, let me draw here. Suppose we have this, right, and here is O and H. So negative charge is here, right? Negative charge is here, to negative charge, so it will shift here. So this bond will shift here, and this bond will shift here, and we will get what? We will get like this. Sorry, we will get here like this, double bond. We will get here like this. One H will be here, another H will be here, right? Now after that, here again this this one, we will take one more like this NaOH. When we are taking here HNO2, sorry, so at that time again this H2O will come out from here, and we will get here the product, which is blue in color, as I have already told you, right? So this was all about the Lieberman's test or nitroso test. And after that we have in your syllabus, it is now next is zinc dust, according to your syllabus. Reduction, or this is also called reduction of phenol. Here it is very simple. We are using here zinc dust. Always remember that the zinc dust we are using, it should be dry. Okay, as you can see, I have already written it should be dry, right? Let me show you. So what is happening here, basically in place of OH, we are getting H. Okay, and ZNO will come out from the reaction. Now again in this reaction also CS3 will be remain as it is. In place of OH, H will come out, or if not, you can also, as you can see, this one is changing into this. Now next is when you are using this one, at that time in place of Z, and when you are using zinc dust here, we will get this OH will come out from here, right? Now after that, last one is oxidation of phenol. So here when we talk about the oxidation of phenol, and like oxidation, electron density will always will be directly proportional to ease of oxidation. Okay, so again when we are taking here phenol, and when we are oxidizing it with N2Cr2O7, and presence of H3O positive, when we are oxidizing this, we will get quinone. As you can see here, we are getting here quinone, right? Now after that, further if you are taking another example here, again in presence of KMnO4, we will get this, right? Now again in presence of this, we will get this, right? So as you can see, so many examples are there. I have already written. You can practice this example, right? Now next is distinguish between alcohol and phenol. Means what is the difference between alcohol and phenol? So we all know that phenol turn blue litmus to red. Okay, red, but alcohol do not, because it is less acidic. Now phenol neutralize base, while alcohol do not. As you can see, in case of this, we will get this, but when we are reacting with this alcohol, at this time we are not getting any reaction, right? It will neutralizing it is, as you can see, phenol is neutralizing the base NaOH, but when we are taking here alcohol, it is not doing anything, the reaction, no reaction, right? Now next is phenol gives, this is also in your syllabus, phenol gives violet color with FeCl3, while alcohol do not. As you can see, it is a violet in color. When we are reacting this phenol with FeCl3, we are getting something like this. So this is violet in color. Okay, NAP plus 3HCl will come out from the reaction. But when we are talking about this ROH and FeCl3, we will get no reaction, right? So I hope you have understood phenols and its property. Now next we will start with ether. Okay, O as a functional group. Okay, and the general formula is what? ROR. Okay, and when where R is what? Here this R will be maybe alkyl or aryl group. Okay, so as you can see, when we talk about the general formula of ether, it will be CnH2n plus 2O, right? As you can see here. Now when we talk about the ether, it may be aliphatic ethers or aromatic ethers. So in aliphatic ethers, in which R and R dash both are alkyl group, means what? If in ether we are write R, O and R like this, right? So if this is aliphatic ether, this R and this R both will be what? Alkyl groups. So right, example of dimethyl ether, we have seen CH3O CH3. So this is an example of what? Dimethyl ether, aliphatic ether or symmetrical ether, as you can see here, right? I have already written symmetrical ether or aliphatic ethers, right? Now next is aromatic ethers, in which either one or both the R and R group are aryl group, right? For example, you can see here, I have already done here, this one is the example here. Okay, or one more example you can take like this. Suppose we have C6H5O and C6H5, right? Diphenyl ether. So I hope you have understood this. Now one more is there. So when this ether may be further be subdivided. Okay, so when we will further subdivide this ether in, we can divide like this: the ether in which one of the group is aryl while the other group is allyl is called what? ALKYL, alkyl aryl ether. Okay, or phenolic ether. May you always try to understand this. If we have ALKYL AROYLETHERS, okay, or this is called PHENOLIC, phenolic. So ether in which one or more aryl ARYL, or while the other is ALKYL, alkyl. Okay, one group is aryl, another group is alkyl. At that time, that type of ethers is called what? Alkyl aryl ether or phenolic ethers. Okay, now next is when in ether in which both the group are aryl, if both the group are ARYL. Okay, so that type of ether is called what? That type of ether is called what? Di-ARYL, aryl ether. Okay, so I will give you one example of diaryl ether. Just you can take the example of C6H5O CS3. This is called what? This is methyl phenyl ether, right? Now next we have also discussed about the symmetrical and unsymmetrical, right? Symmetrical will be when the two alkenes, as you can see, when the two alkyl group is either on the same side, as you can see, either on the same side, the ether is said to be a symmetrical or simple ether. For example, it is already given here. Now again will be unsymmetrical when the two alkyl group is in an ether are different. The ether is said to be unsymmetrical or mixed ether, right? Now next is the structure. As you can see, when you will see the structure, it will be like this, and dipole movement will be here, and dipole movement will be like this. Okay, and when we talk about the bond compound, suppose we have taken here H2O, the hybridization is same, right? sp3, but the bond angle is, you can see here, 104. In case of alcohol, again sp3 hybridization, but the bond angle is 108. But in ether the bond angle is more, as you can see, though it has sp3 hybridization, the bond angle is more, as you can see, 111.7 degree, right? So this was basic idea about the ethers, or basic introduction about the ethers. Okay, now next is nomenclature of ether. So I will try to give you one example. So when we talk about the nomenclature of ether, always remember that when we are doing a common system, at that time ethers named are according to the alkyl group attached to the oxygen atom. Okay, according to the, when we are using a common name at that time, we have to name it according to the alkyl group attached to the oxygen atom. Okay, and here the name of the two alkyl or aryl group linked to the oxygen are written as a separate word alphabetically. Okay, and followed by the word ether. Okay, now again when we talk about the IUPAC name, it will be according to the IUPAC system. Ethers are numbered as alkoxy alkene, right? Ethers are numbered as what? Numbered as ALKOXY ALKANES, alkoxy alkanes, right? Here the large alkyl group forms the parent chain, right? And while the lowest alkyl group is taken as an ethereal oxygen and forms a part of alkoxy group, right? So we will see about this. So here ether, when we talk about the nomenclature, it has two part. One is large part, another one will be small part. So larger part will be alkenes and smaller part will be alkoxy. Okay, and always remember that we have to write the smaller part first and larger part secondly. As you can see, alkoxy alkane, right? See here what is alkoxy alkane, right? So now here you can see one some of the example I have done. So here is what, CH3OC2CH3, right? So this one is ethyl part and this one is methyl part, right? So which one is small? This one is small and this one is large, right? So what we have done, we have seen that the larger part should be written backside and the smaller part should be first. So this one is what, methyl, so we'll add here oxy, so it will be written as methoxy, and this one is ethane, right? In the same way, here you can see chlorine is here, right? So this is chloro for chlorine, and here this methoxy, okay, methoxy methane, right? After that, again in this case, as you can see, this one is called, this is what, anisole, right? Here benzene ring is here attached and here OCH3, right, it is written here, right? And this is called anisole, is what is a common name. So when we talk about the IUPAC name, the IUPAC name is what, methoxy methane, sorry, IUPAC name is methoxy benzene, right? As you can see here. Now next example is this. So how to do this? As you can see, suppose we have given here this group is there, right? So at that time, how we will give the numbering should be 1 2 3 and 4, right? 1 2 3, right? So how we will name, we will write like this. First of all, we will go according to the alphabetic order. So first of all, we will write ethoxy, 3 ethoxy, okay, 1 dimethyl, as you can see. And what is this? This is a cyclobenzene, right? So cyclohexene, right? So as you will, we have written here cyclohexene, right? Now next, this one. So when it is like this is given, wage and days is given, right, in an IUPAC name. So always remember that if this like this wages and days is given, at that time they are asking about the stereochemistry. Okay, they are asking about either the product is trans or cis. So we will see here. So you can see here, when we see the hydrogen, one is below the plane and this hydrogen is above the plane, right? Let me write like this. This is like this, okay? Cl is just above the plane, sorry, Cl is above the plane and hydrogen is below the plane. In this case, this CH3 is above the plane, so CH3 is below the plane and their H is above the plane, like this is there, right? So since this is below the plane and this is above the plane, so how we will number this? We will number 1 2 like this. And now, since this is one is below and one is above, means they are what, trans, right? So we will name here trans. After that, in the first position there is a chloro, so we will write 1 chloro. In the second position, methyl group is here, so we will write methoxy. Okay, how many carbon? 1 2 3 4 means but, right? 4 carbon means it will be butane, right? 4 carbon means it will be butane, right? So as you can see, I have written here. Now next we will see, next we will see this one is what, how we will give the number. We will give, since functional group is here, so we will give him a priority. So how we will give the numbering should be 1 2, okay, So in the first position, in the second position, there is ethoxy, right? So we will go according to the alphabetic order. So we will give 2 ethoxy, as you can written, as it is written, 2 ethoxy, ethane, 1 2 2 carbon, right? Ethane 1, in the first position oxygen is there, so 1 OL, right? In the same way, when you will do this at that time, how we can number this: 1 2 3 4 5 6 7 and 8. So here in the third position there is ethoxy group is attached, right? This one. So we will write here 3 ethoxy. In the sixth position there is methyl group is attached here. As you can see, this one is methyl group. And how many carbon? 8 carbon means octane. So I hope you have understood this, right? Now we will see the preparation of ethane from Williamson synthesis. Okay, so this is a very important because it is given in your syllabus through Williamson synthesis. So when we talk about the Williamson synthesis, this is one of the best method for the preparation of symmetrical and unsymmetrical ethers in a laboratory. Okay, what is happening here? I will give you an overview about this preparation. In this method, an alkyl halide is treated with a suitable sodium alkoxide, okay, prepared by the action of sodium on a suitable alcohol. Okay, and this reaction involve what? Nucleophilic substitution, which is SN2 attack of an alkoxide ion on a primary alkyl halide. Okay, now there are 3 conditions. First condition is if we have RONA, ROR, RLI or ROMGX. Okay, if this R is 1 degree, 2 degree, 3 degree, or alkyl or vinyl. Okay, and if it is reacting with this, but it should be, when we talk about this R should be 1 degree, 2 degree, 3 degree, alkyl, aryl or vinyl, anything. But when we talk about the R which is attached to this halogen, this should be either 1 degree or 2 degree, no 3 degree. If 3 degree will be there, then there will be no reaction. Okay, we will see. And when it will be 1 degree or 2 degree, at that time there will be SN2 reaction, as I have already told you, and it will form ethers, right? This is the first condition. Now second condition is taking here RONA, okay, and we are reacting with this RX. This halogen and this NO will come out as a PPT here, and we will get ether, right? Now next is when we talk about the RX, this R cannot be vinyl. Okay, this cannot be vinyl or aryl. For example, this cannot be this and this cannot be this, because this will go in resonance. Okay, so this should not be R, should not be aryl, the vinyl or aryl. Okay, if R which is attached to this X is aryl or vinyl, at that time it will not form ether, or right? So this was the 3 basic criteria, or we can say that the 3 basic conditions of Williamson synthesis. Now we will see with the retail. Okay, why, if I have already told you, if the R which is attached to this halogen, if it is 3 degree, so why there will be no reaction? As you can see, if it is 3 degree, then there will be a steric hindrance, right? And due to this steric hindrance, there will the RO, the nucleophile which want to attack to this carbon, it will not be able to attack to this carbon, right? Because there are so many groups are attached here, and it will generate an steric hindrance, right? So that is why we are not using here 3 degree or 3 degree, because in tertiary there will be an steric hindrance. Okay, that is why we are not using the R which is attached to halogen. We are not using here 3 degree, right? Now next is, as you can see here, when we are using here CS3ONA, as you can see, CS3ONA in presence of chlorobenzene. So then when we are using chlorobenzene, at that time we will not get this, because chlorobenzene, it will not react with benzene, right? As I have already told you, right? Now again, when we are using this ONA in presence of CS3Cl, it will react, because Cl is a very good leaving group. It will come out from here, and this ONA or negative charge will attack to this, and we will get this, right? But when we are using here chlorobenzene, here it will not react, right? So this is all about the Williamson synthesis. Now again, when 2 conditions, if suppose this type of condition is given, right, in which the Br is here also and here is also Br. So but also always remember that it will not this OCS3, will not react with this Br because here SN2 is not possible. Okay, but here when we talk about this here SN2 is possible because this carbon, when we talk about this carbon is 1 degree here, right? So here SN2 is possible, and this bromine will go in SN2 reaction, as you can see here, right? So this was all about your Williamson synthetic, or some basic idea about the Williamson synthesis, right? Now we will see the reaction. So suppose we are using here RO, and in presence of RX, so what will happen? It will react to form ROR, and X will come out from the reaction, right? So here when we are taking here ROH in presence of sodium, we are getting RONA, or if you are taking here ROH in presence of H negative, we will get RO negative, right? So how to find out RO, we can see here, right? Now next is what we are using here, actual example. We are using here cyclohexane, suppose. Okay, as you can see, cyclohexanol we are using here. When first of all you will see, we will add here sodium. So when we will add here sodium, and then after that we will, in the second process, when you will add CS3 CS2 OTS. Okay, so at that time we will get what? This, right? This is called what? Ethoxy cyclohexane, which is 92%. After that, one more example is here, as you can see. In place of, when we are using this 3,3 dimethyl pentane 2-ol in presence of NaH and CS3I, we are getting what? 2 methoxy 3,3 dimethyl pentane, which is 90% of yield. So this was about the Williamson synthesis. I hope you have understood this, right? So we will see here, some of the question. One question is given, you can try to solve this, and answer is also I have given here. Now one more question is there. So what will be the product of this reaction? So product is written here, as you can see, right? Try to solve this. If you will not understand, then you can tell me. Now next is from ether. From ether, when we talk about this, is also called Williamson continuous esterification process, or by dihydration of alcohol. So here 3 degree, when there is a 3 degree, this will proceed SN1 mechanism. When they say there will be 1 degree and 2 degree, it will proceed SN2 mechanism, as I have already told you. So here when we are talking here ROH and ROH in presence of H2SO4 at 140 degrees Celsius, exact at 140 degrees Celsius, this H2O will come out from the reaction, and we will get here ether, right? But again, you will see in this case, when we are using H2SO4 in the case of 180 degrees Celsius, at that time we are getting ethane, right? But again, when we are using 140 degrees Celsius, at that time we are getting ether. So always remember that in this type of reaction, when we are preparing this ether from alcohol, at that time if we are using here H2SO4, and if S2 and the temperature is above or below the S2 below 140, then they will form if there is an above 140, then it will form ethane, and then when it is exactly 140 degrees Celsius, at that time it will form dimethyl ether, or it will form ether, right? So one example is here, as you can see. In place of Cl, what will happen? There's when we load OH here, at that time in the first place this OH, when this OH negative will come and attack here, and this Cl will come out from here, and we will get this, right? So these are some of the examples I have done for you. Now next is from alkene. So from when we talk about the alkene, from the preparation of ethers from alkene, there are two processes by the addition of alcohol in alkene, and the second process is oxymercuration and demercuration. We have done this in in previous chapter, right? And in haloalkenes and haloarenes also, right? So oxymercuration and demercuration in the preparation of alcohol also we have done this, right? So we will see here by the addition of alcohol in alkene. So when we talk about by the addition of alcohol in alkene, there are two type of reaction. As you can see, there will be a Me2C double bond O when we are taking alkene in presence of H2SO4, so it will form a carbocation here, and this carbocation will further react with this alcohol to form this intermediate here, okay, and this intermediate in presence of H positive, it will form ether, right? So here, as you can see, like this, either this is attacking to this, and this will attack to this, and this will form ether, right? So some of the example is given here, as you can see. Now next one is oxymercuration and demarcuration. So it is very easy. First of all, we are using this with alkene, right? So in presence of HgO8 OAC twice or CS3COO, what we will get? We will get this, right? Hg will come, OAC will come here, and the double bond will break. This double bond will break, right? So now again, when we are taking here, when it will become oxymercuration, when we are using water, as you can see, when we are using here water, it is called what? Oxymercuration. Okay. And now when we are using here alcohol, it is what? Alkoxymercuration, right? When you are using here a alcohol, it is called alkoxymercuration. When we are using here H2 at that time, oxymercuration. So when we are using here H2O at that time, we were getting like this, right? We are getting like this, but when we are using here ROH, we are getting this, right? Now further, in presence of NaBH4, which is called demercuration, we were getting alcohol, right? But here in presence of NaBH, we will again get demercuration, but here we will get ether. So this is the best method to prepare. From this method we can prepare both alcohol as well as ethers, right? As you can see here, for here this is called what? Oxymercuration, demercuration, OMDM. Okay, OMDM. But here we have got what? Alkoxymercuration and demercuration. So I hope you have understood this, right? As you can see, I have done it very clearly. I have shown here, and it is very easy also. In the first case, we were using H2O, this is oxymercuration, and after that, in the second case, we are using OMDM and this NaBH4, so we are getting alcohol. But in here, when we are using alcohol, we are get alkoxymercuration. Okay, and after that DM. So I hope you have understood this oxymercuration and demercuration, right? So here some of the examples are given. As you can see here, some questions are also given. You can do it. Now after that, preparation from alkyl halide. So when we talk about the preparation from alkyl halide, we are using here AgO2, and when we will add Ag2O plus H2O, we will get AgO, right? So here when we are using here 2Rx, and again in presence of Ag2O, when we are hitting this, we will get ROR, and 2Ag plus will come out from the reaction. As you can see here, one we have taken RCl in presence of Ag2O. This should be dry. Ag2O should be dry, because when we are using here Ag2O, it will be moisture. At that time Ag will form alcohol. So Ag2O what we are using, it should be dry, right? As you can see here, dry. So it will form ether, and AgCl will come out from the reaction. So I hope you have understood this also. It is very easy. Now next is industrial method for preparation of this ether. One is this, as you can see, when n mole of ROH, and here n mole of ROH at Al2O3 in presence of 250 degrees Celsius, we will get 2 mole of ROR, which is ether. And if the mass is m here, and here also mass m, then the product mass will be 2m minus 18, because water is coming out from here, right? So water is coming out from here. So as you can see, some of the example is given here, how the industrial method for preparation of ethers, right? No. Next we will see the chemical property. So for chemical property, why its first question is why ethers are never heated to dryness. As you have seen, if you will see the in our lab, the ethers, it has been also written there, never heat to dryness, because it is very explosive when it is when you are drying this. We will discuss about this, as I have one example I have written here. When we are using O2 in presence of dryness, it will be explosive. So the first is reaction with ethers. Reaction of ethers with HX, or we can say here X is what? Here X will be either iodine, bromine and chlorine, not fluorine. Okay. So here we can see we have used here tetrahydrofuran. As you can see here, excess, we will get here this, right? 1,4-dibromobutane. When we talk about the mechanism here, this O is shifting here, right? And this bond will break, not this. This bond will not break, this bond will break, okay? And we will get this, right? Now if this is the condition, phenyl group is attached to this oxygen, vinyl group or reso group is attached to this oxygen, at that time this bond will not break, okay? As you can see, one example is given here. Right now, when we talk about the SN1, it will 3 degree. If there is a 3 degree, then it will go on SN1, and if there is 2 degree and 1 degree, it will go SN2. Right? And benzyl allyl, here it will attack to small OH, and if there is 2 degree and 1 degree, it will attack to large OH. Okay. Now some of the example is given here. As you can see, it is small and this is large. After that, when you're in presence of H positive, this I, because this I will attack to this CH3. Okay, and this bond will shift here, and after that, this is an SN type, SN2 type, right? Because it is attacking from the back side. So the final product, we will get CH3I and C2H5OH will come out from the reaction. In the same way, in case of this also, this I will, because in the first case, in the presence of H positive, we will get this bond will shift here. Okay, and we will get like this CH3H, and we will get this positive here. So now this negative, this I will come and attach to this, and we will get this, right? So this was about the chemical properties with preparation with HI. Now there is oxidation, as I have already told you, or we can say this is also called peroxide formation. So it is a very explosive. As you can see, on exposure to the sunlight, ether slowly react with the oxygen from air to form hydroxy peroxide, hydroperoxides of peroxide, which are explosive, as I have already discussed you. And this is the reaction, as you can see here, right? Now again, the last one, reaction with PCl5. This is the last from your syllabus point of view. So here we will see that when it is reacting with when we are taking here dimethyl ether, and when we are reacting with this PCl5, when we are heating this, we will get what? Ethyl chloride will come out from here, and we will get here perchloric acid. Okay, phosphoric chloride. Okay, as you can see here, phosphoryl chloride we will get here. So I hope you have understood this chapter. Okay, in case of any doubt, you can contact me on my personal number, and here I have attached all the notes of this chapter, as you can see, from the beginning, from where I have started to teach, right? As you can see, you will get each and every syllabus. This notes I will give you in your group. Okay, I will send you this notes in the group. As you can see, each and every topic which I have covered, it is there. And in this chapter, in this notes, there are some of the important questions for your exam, also exam point of view, and some of the topic is extra for NEET point of view for your NEET exams. So no need to do this. If you want, you can do. Okay, but the thing which is given in your syllabus, you go through the syllabus and mark all the important topics which is here. Okay, and go through this chapter. In case of any doubt, you can write in the comment section, or you can contact me on my personal number. Okay, till that, thank you.